this third lecture, I'd like to begin by circling back a little bit and discussing the degree to which dimension 4 is extremely peculiar for certain aspects of Riemannian geometry in a way that people did not appreciate until sometime in the 1990s. And even then, I think that many of these things are better known to certain topologists than to Riemannian geometers, and therefore the following simple points have not really been emphasized enough. I hope it will be useful for me to begin by considering a particular variational problem. So if you have a smooth compact N manifold, and I'm always assuming that the dimension is not 2, it's at least 3 for this discussion. We can then consider so we have a fixed smooth structure, we can consider the set of all smooth Riemannian metrics on our given manifold, which I'll call G sub m, since G is the usual letter for denoting metrics. As I mentioned before, that's really Einstein's notation for the gravitational field, but who cares? It's what we call metrics, usually G. So the Einstein metrics are critical points of the following scale invariant action functional. So what you can do is assign to every metric the integral of the absolute value of its scalar curvature to the power n over 2 integrated on the manifold. If you like, what you're doing here is you're taking the LP norm of the scalar curvature to the pth power, where p is n over 2. Now, that's a strange looking power, perhaps, in most dimensions, but it has a privileged place. So here, of course, in my notation, little s in red always denotes the scalar curvature, and that's by definition the trace of the Ricci curvature, or of the Ricci tensor, and if you like, it's the full trace of the Riemann curvature tensor. And I also told you that the synthetic meaning of the scalar curvature, or one synthetic meaning of it, is that if you take a Riemannian ball of radius epsilon, so all the points in the manifold you can reach from the base point P by a curve of length less than or equal to epsilon with respect to the given metric. Take the volume in the manifold of the ball of radius epsilon around P, divide by the corresponding answer in Euclidean space, where this C sub n is a well-known constant you can calculate. So the ratio between the Riemannian volume and the Euclidean volume has a Taylor series expansion, so to lowest order it's 1. Then there's a quadratic deviation of order epsilon squared. Epsilon is the radius, and the coefficient is minus the scalar curvature times the constant dependent upon the dimension. So the scalar curvature here, I've said it's the trace of the Ricci tensor, but remember that to take the trace of the Ricci tensor, you have to use the metric. It's the trace with respect to the metric. In here, G with upper indices is the inverse of the metric with lower indices. So the Ricci tensor does not actually, if you rescale the metric, it doesn't change the Ricci tensor. It doesn't change the curvature tensor, but when you perform this trace to get the scalar curvature, you are explicitly using the metric. And so if you rescale the metric by multiplying it by some say positive constant squared, in other words, if you change the metric to make all lengths in the manifold bigger by a factor of c, then the scalar curvature rescales by the inverse of that c squared factor, and that's exactly because you're using the inverse of the metric here to compute the scalar curvature. And the volume rescales by c to the n times the, it's rescaled by c to the n. And so this factor of taking the absolute scalar curvature to the n over 2 is exactly chosen so that these two effects cancel. Right? So if you're asking for what p is the LP norm of the scalar curvature invariant under multiplying the metric by a constant, that happens exactly for this value of p. And so, by the way, there are many Riemannian functionals where you would see this the power is half the dimension in order to make the function scale invariant, where scaling means invariant under multiplying the metric by a constant. So, the first claim is that an Einstein metric is a critical point of this functional, and conversely, that is almost a characterization of Einstein metrics. There's one other class of critical points which we'll have to think about. So, of course, this looks particularly nice in the four-dimensional case where we're simply talking about the integral of the scalar curvature squared. And you may remember we've seen various Gauss-Bonnet type formulas for characteristic numbers in terms of curvature, and the integral of the curvature of the scalar curvature squared is one contributor to those kinds of formulas. So if we wanted to find out, so if you think about the space of smooth metrics as an infinite dimensional Chaire manifold or something like that, then you can ask what's its directional derivative in any direction, since it's an open subset of just the vector space of smooth tensor fields of the appropriate type. We could just say, what happens if we move along a straight line by adding on another tensor field h times t to the given metric, and then there's a very standard calculation. How does the scalar curvature, what's the first variation of the scalar curvature? You take the derivative with respect to t of the scalar curvature and evaluate at t equals 0, then it's not hard to show that the contributions are the Laplacian. This is the positive spectrum Laplacian applied to the trace of h with respect to the metric g. And then you have another term which is double divergence of h, and then finally a contraction with a minus sign, the contraction of h with the Ricci curvature, the inner product of h with the Ricci curvature. On the other hand, the volume form also, of course, changes. The first order the change of the volume form is that the first derivative is the trace of h times 1/2 times the background volume form of g. If you put these together and now ask what's the derivative of this expression with respect to t at t equals 0, the answer comes out as follows. So we saw an expression for the first derivative of the scalar curvature before, but the difference here is that, remember, this is scale invariant. It turns out that the change in the volume form exactly cancels out the trace term here. And so you get that sort of expression, but only involving the trace-free part of the Ricci tensor. And then all of that is times the following expression. So it's s to n over 2 minus 2 times s. A different way of writing that, which makes it clearer that this is a continuous function of s, even if n is equal to 3, is that it's the absolute value of scalar curvature to the n over 2 minus 1 times the sign of s. All right, so I will tend to write it this way. If you write it this way, it's less obvious that this defines a continuous function when the dimension is 3. In high dimensions, it's pretty obviously a continuous function. So what is the condition for this this variation to be 0, no matter which choice of h we make? Well, the first class of h's you might take would be if you change it. If you imagine staying in the same conformal class, just multiplying your metric by a function, then in first order what you're asking is what happens if I add on u times g, where u is some arbitrary smooth function. It doesn't have to be positive, just a smooth function. So that previous expression simplifies now, and what you get is, well, we have that funny function of s of the scalar curvature times the Laplacian of u. If this is if this is 0 for all possible choices of u, then you're actually, so if you're thinking in terms of distributions, what you're doing is you're taking the distributional derivative of this function and then taking its L2 inner product with u. So if you, so in fact, to be a critical point, then this function of s has to be in the kernel of Laplacian, if you think of it as a distribution, but this is already a continuous function, so elliptic regularity immediately tells you this is actually a smooth function, and it has to be a harmonic function on the manifold, but your manifold is compact, so the maximum principle says it has to be constant. And so, so any critical metric, that function of s is constant, but that's actually the same as saying the scalar curvature has to be constant for any critical point. But then that allows us to simplify our analysis. From now on, we can assume the scalar curvature is constant. And now, assuming the scalar curvature is constant, we just pull that messy expression in the scalar curvature out. It's just some constant. And what's left over is that second order expression that came up when we looked at the first derivative of the scalar curvature, with the only difference that you don't see the full Ricci tensor here, you only see the trace-free part of it. And so, in fact, the first variation, having already observed that for a critical point, the scalar curvature has to be constant, you find that the critical point condition is that this constant times the L2 inner product of this tensor H, arbitrary symmetric tensor with the trace-free Ricci tensor, would have to vanish. But of course, we could have taken H to be the trace-free Ricci tensor itself. And so that says the condition is that, the condition for it to be a critical point is that either this constant is 0 or the trace-free Ricci curvature vanishes. And so the conclusion is that what are the critical points of this? By the way, little exercise. I didn't really labor this point, but when you could worry at first, is this actually a differentiable function of the metric? It is. I actually just wrote down what the derivative is. So the critical points of this functional are exactly the Einstein metrics and also the scalar flat metrics. If you have any metric on the manifold whose scalar curvature is identically 0, then that's also a critical point. If you think about just the case, if it's in dimension 4, you're looking at the integral of scalar curvature squared. Well, obviously, if scalar curvature is 0, then any first variation of that is that you won't get, you just get 0 as the derivative, right? Because it's quadratic in s. If s is initially identically 0, then you have a critical. Now, this is not the only functional that people like to think about. There's a closely related functional called the Einstein-Hilbert functional. I'll talk about that in a different lecture. But the nice aspect of this particular functional is it is non-negative. And its critical points are either Einstein metrics or metrics with scalar curvature identically 0. So for this particular functional, there's a naive thing that one could try to do to find an Einstein metric on a manifold. You could try to minimize it. Right? It can't go lower than 0. So what happens if we try to minimize this functional on the space of all metrics? Well, after all, that's a difficult analytic problem. When you have these variational problems, there's no reason to believe there's actually a solution. That comes down to a lot of very interesting analysis, in this case, of nonlinear elliptic PDE. However, just that idea, for completely soft reasons, gives you a natural, smooth invariant of a compact manifold. Namely, well, so we take this function along all metrics, and we take the infimum along all metrics. Independent of the question of whether there's a minimizer or not, we certainly have, there's a well-defined infimum. The function is non-negative, so there's some non-negative number associated with the manifold by this process. And so we have an invariant which I call I sub s of m. The s here is my notation for the scalar curvature. What's I? Well, it's an interesting integral infimum invariant. I choose your I. Invariant, though, is the primary one I'm thinking about. Invariant defined in terms of the scalar curvature. And this just depends on the smooth structure of the manifold. If you have just a topological manifold and it has various smooth structures, there's no reason to believe that you would get the same infimum for the different smooth structures. A priori. And we'll see. Eventually, yes, it does. In the four-dimensional context, this gives rise to a non-trivial invariant. But this is an example of a soft invariant. It's not defined by saying we have some elaborate theory of how to compute it. It's just pure thought says every manifold you can associate this number. And what often happens in mathematics is that if you use just pure thought to define some kind of invariant, well, it could be extremely difficult to compute. So, any beginning graduate student first learning about homotopy groups really loves homotopy groups because the definition is very easy, but you find out they're really hard to calculate. Homology is much more calculable, and it's only by using a lot of knowledge of homology theory and other things that you ever get a handle on homotopy groups. So the basic question is, so we've defined some number. Is it calculable? Is it sort of non-trivial? What could you say about this? So the first theorem is, suppose that we have a compact, simply connected manifold. And here, there's no reason in general to only consider simply connected manifolds. And this can be, but for the purposes of these lectures, I've been concentrating on the simply connected case. I've discussed simply connected four-manifolds at great length in the last lecture from the point of view of just as topological spaces. So if we have a smooth, compact, simply connected n manifold, where n is greater than or equal to 3, then if n is not equal to 4, this invariant is 0. And this is not a trivial fact. It doesn't happen for easy reasons. There's a constellation of things that come together. If you're not in dimension 4, the invariant that we've just defined is actually 0. So one key ingredient is the following important fact. Suppose you have a smooth, compact manifold. We always assume we're not in dimension 2. If it admits a Riemannian metric of positive scalar curvature, then it also admits a different metric whose scalar curvature is identically 0. This has to do, I'm not really going to talk about the Yamabe problem and Yamabe invariance today, but this actually comes down to how does the Yamabe constant vary as you vary through different conformal classes of metrics. And I will talk about that in the next lecture. So this is a slightly not obvious fact. If you have, for example, if you're on the standard 3 sphere, that has an obvious metric of positive scalar curvature. It turns out there's also a 0 scalar curvature metric on the 3 sphere. In that case, you can actually construct examples very, very concretely. But there's a nice kind of pure thought proof of this once you've mastered the theory of Uabi constants of conformal classes. So on the other hand, amazing work of Gromov and Lawson in the early 1980s showed that if you had a compact, smooth, simply connected, non-spin manifold, so you assume that you're in a dimension greater than or equal to 5, then there are metrics of positive scalar curvature on it. And in particular, by this previous claim, that means there are metrics of scalar curvature identically 0 on it. But that means that this infimum must be 0. Plug in a metric where the scalar curvature vanishes. So I won't really try to explain how this proof goes. This is a wonderful theorem, and the key lemma is that they show if you have a manifold and you perform surgery on it, you take an embedded sphere whose codimension is at least 3, you then can cut it out and replace it with a sphere of complementary dimension. So, it would, if its codimension is k, then you replace the sphere with a k-1 sphere. And there's a standard way of doing that. So that, if you haven't thought about cobordism theory, that surgery, it turns out any cobordism is gotten by applying a sequence of surgeries, but here you have this extra constraint that you're only allowed to do surgeries in dimension 3. Under that operation, it turns out that the condition of having a positive scalar curvature metric is invariant under those kinds of surgeries, and what they're able to do is reduce this problem to a question in cobordism theory, which they could solve in the non-spin case. My student, Jimmy Patian, then proved a theorem in the late 90s, which beautifully improves this statement. Suppose that instead of saying, suppose the condition is a positive scalar curvature metric, suppose you impose the condition that there is a metric for every positive epsilon, there is a Riemannian metric whose scalar curvature is greater than or equal to minus epsilon, and where the volume of the metric is 1. Jimmy's key lemma was to show that this is also invariant under codimension 3 surgeries in the same way, and then so he reduces this problem again to a question about cobordism theory, and some work by Stefan Stolz in the meantime about the spin case had revealed more things about the existence of positive scalar curvature metrics in the spin case. It's related to things I'll tell you about later on. And so ultimately, that ends up showing you that this invariant is in fact 0 for all simply connected n manifolds if n is bigger than 5. So in higher dimensions, simply connected manifolds, there's no life on this planet. Now there's one other dimension in which I made this assertion. What happens in dimension 3? Well, Perelman and people that carefully went through his papers and corrected everything and wrote it out in detail. Perelman's work in particular implies the Poincare conjecture. The only compact, simply connected, smooth 3 manifold is the standard 3 sphere. And I've just pointed out on the 3 sphere, yeah, this invariant is certainly 0. And it's again because of this statement, if there's a positive scalar curvature metric, there's also a metric whose scalar curvature is identically 0. Right, so there would be no point in discussing this topic at all if it didn't turn out that the story is completely different in dimension 4. And it seems to me almost magical that 4 dimensions is so strange. This simple natural problem turns out this is a highly non-trivial functional leading to a highly non-trivial invariant in dimension 4, and at least for simply connected manifolds, leading to 0 in other dimension. So in fact, the statement is, so remember, if you had a metric that minimized this functional, it would have to be Einstein. So there exists there's a sequence of compact simply connected four manifolds, MJ, in fact, many ways of constructing such sequences, such that this invariant goes to plus infinity. And you can even choose these manifolds so that this infimum of the integral of the scalar curvature squared is realized by an Einstein metric with lambda negative. These are all actually negative scalar curvature Einstein metrics. The infimum is actually a minimum on a sequence of manifolds where this invariant goes to infinity. So the point again is that 4 dimensions is completely exceptional. Yes?
Is it easy to see that the infimum is attained by something which is Einstein constant negative?
So the pure thought thing is that if you had a metric that minimized this functional, and if the minimum was not 0, then it would have to be Einstein. That was really the computation I went through about the critical points. So certainly a minimum has to be a critical point. And so at a non-zero value of the functional, if you have if the minimum is actually positive for the integral of the scalar curvature squared, and you have a metric that is a minimizer, then that metric is an Einstein metric. All right, so here's the underlying, really surprising theorem. Suppose that you have a 4-dimensional manifold which admits a Kähler-Einstein metric with lambda negative. So Kähler-Einstein means, and some people get confused about this because some people's exposition is so bad that students are left being confused. Is a Kähler-Einstein metric actually an Einstein metric? Yes. Yes. Kähler-Einstein metrics are exactly Einstein metrics that are also Kähler metrics. And the reason that it's confusing is that the formalism that one tends to work with for treating Kähler-Einstein metrics is never actually to talk directly about the metric, but to talk about the Kähler class. And at the end of the day, you could be so confused as to not really understand this simple point. Okay? So the class of Kähler-Einstein metrics is exactly the set of Einstein metrics that are also Kähler metrics. And a Kähler metric is something where the holonomy is in the unitary group. You can associate to such a thing an integrable almost complex structure. And here I've put this in explicitly. So we're talking about there is a choice of complex structure on this 4-manifold, making it into a complex surface. On that complex surface, we have a Kähler metric, which is an Einstein metric with negative Einstein constant. All right, then actually, this Einstein metric is an absolute minimizer of the integral of the scalar curvature squared. And so it achieves this infimum invariant. Now, this is, and moreover, it's not like this number that you're going to get is something that is mysterious. It's just written in terms of a simple topological invariant of M, for reasons I'll explain later on. It's because we mentioned that this number 2 chi plus 3 tau of M is actually this is the first Pontryagin number of lambda plus. If you we'll see it simple computation, that means that number is also C1 squared of any almost complex structure on the manifold. So anyway, using some knowledge of very elementary things about Kähler-Einstein metrics, if you have such a Kähler-Einstein metric, the integral of scalar curvature squared is 32 pi squared times 2 chi plus 3 tau of the manifold. So that's, it looks like just a homotopy invariant of M, but there's something interesting and subtle happening. Now, the proof of this depends upon Seiberg-Witten theory, which I'm going to start explaining to you today. Seiberg-Witten theory is a theory that can only be formulated in 4 dimensions. This proof does not work in other dimensions. And so the thing, you might feel cheated if you know that in higher dimensions there are lots and lots of Kähler-Einstein manifolds with lambda negative. And on the other hand, if you just think of those as Riemannian manifolds, you think about not just varying through Kähler metrics, but varying through arbitrary Riemannian metrics, they don't have this special privileged position in higher dimensions that they have in dimension 4. In dimension 4, they minimize the integral of the scalar curvature squared. If you go into higher dimensions and you ask, do they have any special status with respect to the scalar curvature, the answer is no, they don't. So, just to make it very concrete, I'll wind back and make it clear to, if it's not, for some people in the audience, it'll be dead obvious why these are examples, but I'll come back and explain the parts of the magic trick in a moment. We've already seen a sequence of 4 manifolds that fulfills this that gives us some nice, some 4 manifolds where we can actually find these Einstein metrics. Namely, suppose you take a hypersurface in CP3 given by a generic homogeneous polynomial of degree n, where n is bigger than 4. So here I wrote down the Fermat hypersurface of degree n, and so n is in purple here, it's not the dimension. It's the degree of this hypersurface. And the Lefschetz's hyperplane section theorem implies these are all simply connected manifolds for all n. And if you calculate, I claim that each of these has a Kähler-Einstein metric with lambda negative, and if you now compute that invariant, it's 32 pi squared times, well, this is C1 squared of the manifold, and it turns out that's n times n minus 4 squared. Obviously, as n goes to infinity, this goes to infinity. So that the claim I've just made, if we could verify all that these have metrics and the Kähler-Einstein metrics in dimension 4 have these properties, this very simple family of examples already proves that claim about dimension 4. So the key existence result that one needs is was independently proved by Aubin here in Paris and by Yao at the time he was in the United States in those days. And it's known as the Aubin-Yao theorem. If a compact complex manifold M2Mj admits a compatible Kähler-Einstein metric with S less than 0, so that's the same as saying that lambda is less than or equal to 0. Remember, the Einstein constant has the same sign as the scalar curvature of the Einstein metric. If and only if its first Chern class is, quote, negative. And this is one of those things where every graduate student who sees C1 negative for the first time wants to scream. C1, that's a cohomology class. What does it mean to say that it's negative? This is actually saying that that C1 is represented by minus some Kähler class. But concretely, it's actually saying the canonical line bundle is ample, which means the following thing, that there is a holomorphic embedding of your complex manifold into some perhaps possibly large dimensional complex projective space, such that the first Chern class is a negative multiple of the pullback of the first Chern class of the projective space. If you're familiar with these things from a different point of view, what I'm really saying is, so one way of saying it is that C1 of the canonical line bundle is ample. It has lots and lots of sections, or some sufficiently high power. It has lots and lots of sections. And by the way, a different way of making the negative multiple, you could also say it's a negative multiple of the standard generator of the first homology of CPK, which just differs from this by a positive factor of k plus 1. All right, so we're interested specifically in the. Notice that this works, in high dimensions too. There are lots and lots of Kähler-Einstein metrics in high dimensions. Lots and lots of Kähler-Einstein metrics with lambda negative on simply connected manifolds. If we had started, rather than with CP3, we started with CP4, CP5, took hypersurfaces of large degree. Those would be, those would give us complex manifolds that emitted negative lambda Kähler-Einstein metrics, but they would not have any special property in the space of all Riemannian metrics. They would not minimize the function we were talking about. In dimension 4, that's the magic. So a different way of describing what are the complex manifolds where you can find such a metric. If you're in the complex surface case, so the real dimension is 4, the complex dimension is 2, then they are the minimal complex surfaces of general type in which you can't find an embedded CP1 of homological self-intersection minus 2. A different way of saying that they're the complex surfaces of general type such that you can't find an embedded CP1 whose homological self-intersection, remember the intersection form last time, is neither minus 1 nor minus 2. If you have an embedded sphere of an embedded holomorphic CP1 with self-intersection minus 1, it turns out it can always be blown down. So the notion of minimal is saying you can't blow it down. But there's this, that turns out to be a more differential topological condition. The existence of, or non-existence of minus 2 curves is more delicate and is actually not invariant under complex deformations. All right, so the summary is that the first property that such a complex manifold has to have is it is of general type. Then it's also minimal. It's a minimal surface of general type, and it has this auxiliary condition. There's no embedded CP1 of self-intersection minus 2. So let me remind you that there's this notion of blowing up. If you have a complex surface, you can replace a point by a CP1 to get a new smooth complex surface where the normal bundle of this inserted CP1 is the Chern class minus 1 holomorphic line bundle on CP1. And that ends up changing the diffeotype by taking a connected sum with CP2 bar. So we saw that picture before. So a complex surface is called minimal if it is not the blow-up of another complex surface. And so if you have any complex surface, let's say M, it's a piece of pure thought. It can, if it's not minimal, you can blow it down. And you can continue blowing down as many times as possible. That's always, and most finitely many times, because that reduces the second Betti number by 1 every time you blow down. So it's a little observation made explicit by Kodaira, but it kind of goes back to people like Enriquez, that every complex surface can be obtained from a minimal complex surface by blowing up a finite number of times. And so in particular, you can represent any complex surface up to diffeomorphism by a minimal complex surface connected sum with a certain number of copies of CP2 bar. If k is 0, it's a minimal surface, otherwise you've blown it up a certain number of times. And then in this circumstance, one says that this minimal surface that you got M from by blowing up is called a minimal model for M. And this is actually unique if the Kodaira dimension is not minus infinity. And finally, the Kodaira dimension of any complex surface is the same as the Kodaira dimension of its minimal model. And finally, If you deform a complex surface, it does not change its Kadeira dimension. All right, so the statement, when I said talked about complex surfaces of general type, those, a complex manifold is said to be of general type if its Kadeira dimension is the same as its complex dimension. In the case of compact complex surfaces, that's to say that when you look at the dimension of the space of, take the canonical line bundle, and you can take its Lth tensor product where L is positive, and ask how many, what's the dimension of the space of sections of that line bundle. So the canonical line bundle on a surface would be the bundle of two zero forms. It's, if you like, if you think of the cotangent bundle as a complex vector bundle of, here would be a rank 2, you're taking its highest wedge power. There's a line bundle you can get by taking the determinant line bundle of the cotangent bundle. And this so-called canonical line bundle turns out to give rise to a lot of important invariants. These particular invariants, I haven't written down what the name is, these are usually called the plurigenera of your complex manifold. So in the case of complex surfaces, to say that it's of general type is to say that this dimension of that space grows quadratically as you take the power of the canonical line bundle going to infinity. Okay, so I mentioned the Kadeira classification of complex surfaces before. I mentioned that this Kadeira dimension plays a fundamental role. It is the growth rate of the space of holomorphic sections of powers of the canonical line bundle. It turns out that the way that these grow is roughly like a polynomial, and the degree of that polynomial is called the Kadeira dimension. But so the Kadeira dimension, it turns out, is in fact always either an integer between 0 and the complex dimension, or it's minus infinity. And the better explanation of this is exactly the same among all of the maps to projective spaces you get by looking at holomorphic sections of a positive power canonical line bundle. The Kadeira dimension is you take the image of M, look at the dimension, complex dimension of its image, and the maximum such dimension is exactly the Kadeira dimension. So if you can find a power of the canonical line bundle where this map to projective space had dimension 2, that would exactly say that it is of general type. You have maximum Kadeira dimension. And here we have in order to make this statement strictly true, we have the weird convention that we define the dimension of the empty set to be minus infinity. All right, so let's just see how the Kadeira classification of minimal complex surfaces. So the first simplification that Kadeira imposes is, well, we know any complex surface is the blow-up of some minimal surface. So let's just try to classify the minimal surfaces. And so if it turns out that the case where B1 is even consists exactly of complex surfaces that admit Kähler metrics. This is obviously it's a classical fact that if you have a compact complex manifold that admits a Kähler metric, then its first Betti number is even. An amazing converse is that in complex dimension 2, if B1 is even for a compact complex surface, it actually admits Kähler metrics. That's highly non-obvious. Involves a lot of hard work. All right, but just assume B1 is even. What are the possibilities? So the Kadeira dimension could be minus infinity, and in that case, well, CP2 is an example. Also, you could have a CP1 bundle over a curve. So, for example, you could have CP1 times CP1, you could have CP1 times a curve of genus 2, CP1 times a curve of genus 25, all right? all of those have Kadire dimension minus infinity, and it turns out in the Kadire classification it's not quite that these are all products of CP1 with something, but they're all CP1, holomorphic CP1 bundles over some Riemann circles. Okay? Among these, the invariant C1 squared, and that's 2 chi plus 3 tau, that can have various signs depending upon if it's CP2 that has C1 squared positive, if it's CP1 times the surface of genus 2, that would have this invariant would be minus negative. If it's CP1 times something that looks like a 2 torus, that would have C1 squared equal to 0. If the Kadire dimension is 0 and V1 is even, then the only possibilities are K3 surfaces, complex tori of complex dimension 2, and things that are finitely covered by those. Remember, those are exactly the kinds of manifolds that came up in the borderline case of the Hitchin-Thorpe inequality. So in this case, C1 is actually 0 for these manifolds. C1 squared is 0. If the Kadire dimension is 1, the things you see are, if you have a complex surface which has a holomorphic map to a Riemann surface, and the generic fiber is an elliptic curve, in other words, something that's topologically a 2 torus, then those turn out to have in most cases to be of Kadire dimension 1, and in most cases have V1 even. All right, so again, for the minimal surface here, that you would have C1 squared is 0. And then in the case of general type, you would actually have, the Kadire dimension would be 2, and then C1 squared would be positive. If B1 is odd, so this is the realm where Kadire completely invented the field. Before Kadire, this notion, these kinds of classification ideas had been used by the classical Italian school of algebraic geometry, but it was always for things that were algebraic varieties, and in particular, they all admitted Taylor metrics. When B1 is odd, and that's something impossible if there's a Taylor metric on it, well, you can, the ones of Kadire dimension minus infinity are said to be of type 7 in Kadire's classification. The most familiar example, if you know what a Hopf surface is, which is topologically S3 times S1, those guys belong in this slot. There are certain T2 bundles over T2, which have Kadire dimension 0, but have B1 odd. And then there are also some examples where B1, when B1 is odd, then there are certain elliptic vibrations over curves. Notice that for all of these, either C1 squared turns out to be 0, and this number is 2 chi plus 3 tau. So the Hitchin-Thorpe inequality would say that if you had the underlying Four-Manifold here, if it carried an Einstein metric, it would have to be diffeomorphic to a K3 surface or a 4 torus or something covered by that. And you can show that these are all topologically different, the wrong topology. None of these, they are interesting from the point of view of complex surface theory. They never are interesting from the point of view of Einstein metrics. None of these Four-Manifolds admit Einstein metrics, even if you say don't require the Einstein metric to have anything to do with the complex structure. So C1 squared turns out to be 2 chi plus 3 tau. If you were to say, well, this is the number you want to be positive in the non-boundary case of the Hitchin-Thorpe inequality, that for a complex surface it turns out to imply that either the Kadire dimension is minus infinity or it's 2. And there's an argument of Grauert, which I really won't go into, the key point is that if you look at the index looking at the number of sections of K, or the dimension of the sections of K to the L, well, you might try to understand that in terms of the index. One contribution is the the dimension of the space of sections of K to the L. You also have other contributions, which you can understand in terms of serduality, in terms of negative powers of the canonical line bundle, and then there's a first cohomology. Anyway, the key term that comes in here is C1 squared. So if C1 squared is positive, you end up concluding that for large L, this will be positive, and you end up either having a lot of sections of K to the L, or dually a lot of sections of a negative power of the canonical line bundle, and those correspond to canard dimension 2 or canard dimension minus infinity. All right, so I've emphasized that that C1 squared actually, I've just claimed C1 squared is the same as the first Pontryagin class of lambda plus. I should have written down the formula. The point is that if you're looking at lambda plus, if you assume that G is Hermitian, for example, it's Taylor. And here I'm just saying that there's an almost complex structure where the metric is invariant under J. And this J could even just be, it doesn't have to be integrable, it could just be an almost complex structure. Then you can actually write lambda plus as, well, there is an associated form like the Kähler form. In the Kähler case, this would be the Kähler form. So the real span of the Kähler form, that's something in the two forms. And then you have the real projection of the canonical line bundle. So as a bundle, as a real bundle, lambda plus on a complex manifold of real dimension 4 turns out to have a trivial direction, and then so this is of rank 3, and this three-dimensional space has one direction which corresponds to the span of the Kähler form, or the analog of the Kähler form if it's not closed. And then you have a perpendicular plane where if you equip this with the natural almost complex structure, but just by rotating in this oriented three-dimensional space, this is really just the canonical line bundle. So a form of type 2-0, a different way of saying this, if I complexify the self-dual forms, that looks like a trivial complex rank 1, or looks like a complex line bundle, plus the forms of type 2-0 and the forms of 0-2. These two are conjugate. And if you now look at the real things, there's a real projection of this, which gives you something of real rank 2. All right, so what's really going on here, if you think about what is the first Pontryagin number of the first Pontryagin class of lambda plus is the same as minus C2 of the complexification of lambda plus. And in this case, you'd be looking at saying what is minus C2 of something trivial plus the canonical line bundle plus the conjugate of the canonical line bundle. And then when you work it out, you'll find that this is then C1 of the canonical line bundle squared, and that's the same as I put a conjugate here, and that's the same as C1 squared of, so this is the determinant line bundle of the tangent bundle, so this would be the same as your almost complex manifold. Take the first Chaire class of the complex tangent bundle, C10 tangent bundle, then you take its first Chaire class squared. That would give you the first Pontryagin number of lambda plus, but then we've seen that this is the same as 2 chi plus 3 tau of n. So if you take it for granted, this statement that I that I made last time, that 2 chi plus 3 tau of m is exactly the first Pontryagin number of lambda plus, well, you see that this is calculable in terms of taking the first Chern class of an almost complex structure and squaring it, and then evaluating, and then pairing that with the fundamental cycle. All right, so if you were to ask which complex surfaces could admit an Einstein metric, well, you'd have to have C1 squared positive. And so the other observation is what happens if you blow up, if your surface is not minimal, it's the blow up of some minimal model, then there's a relationship between C1 squared of the minimal model and C1 squared of m. Namely, it's the C1 squared of the minimal model minus k. So even if m admits an Einstein metric, and it's, let's say it's one with this, where lambda is non-zero, this would be positive, but then that would force C1 squared to be positive too. Right? So C1 squared is actually bigger than, if it's actually non-minimal, its minimal model would have a larger value of C1 squared. So if you're looking in this range, where could you look for four manifolds among the complex surfaces which might admit a Kähler metric? Then you would actually always be in the case, except we've talked about flat things and Calabi-Yau things last time, where the Kadari dimension would be 0. Otherwise, you're either in the case of general type, where the Kadari dimension is 2, or the case when the Kadari dimension is minus infinity. All right, so when we looked at the Hitchin-Thorpe inequality, we saw that, except when if we have an Einstein metric on a four manifold, if it's not locally hyperkähler, then you'd actually have 2 chi plus 3 tau would be positive, and going back to the previous slide, that would be saying that C1 squared is positive. All right, so in fact, in particular, you would find that your manifold, if it admitted an Einstein metric, lo and behold, and it's also a complex surface, it's actually one of Kähler type. Okay. So the Hitchin-Thorpe inequality ends up telling us that if we have a compact complex surface that admits an Einstein metric, even an Einstein metric having nothing to do with the complex structure, if the Einstein constant is non-zero, then actually the Kadari dimension is either minus infinity or it's 2. And moreover, M is a Kähler type. In particular, it admits a symplectic structure. So these two cases are called, would be surface of general type, and it'll turn out that when we look more carefully at this case, you can narrow it down. They're actually things called rational surfaces, which we will discuss in another lecture. All right, so it's time for a break. Let's go have some coffee and well, I know that these meetings are very long, and I definitely am grateful for your endurance, but in order to break it up a little bit, maybe it's nice to give you the opportunity to ask questions. Do you have any questions about the first part that you'd like to raise now? Yeah.
A small question about G.B. Betham's result. You said that you showed that there is a metric where the scalar curvature is at least minus epsilon.
For any epsilon, yeah.
Right. But is it non-positive, or because if it can be positive?
Well, it can be positive in some places, but it won't be positive. So it'll turn out that in many cases there's an obstruction. So if this allows the metric, the manifold could be, for example, a spin manifold where the A hat genus was non-trivial, or there's a Hitchin genus in certain dimensions. So A hat genus is only defined if the dimension is divisible by 4, but if mod A, the dimension is 1 or 2, you also have this Hitchin genus. His essential mission there, so what Stolz had previously done is he had shown that in the spin case, the only, among simply connected N manifolds where N is at least 5, that there was a positive scalar curvature metric unless it was a spin manifold where the Hitchin genus or the A hat genus was non-zero, and therefore you had an obstruction. So the known obstructions turned out to be the only ones in the simply connected case. The trick that Jimmy Paitian discovered is that, first of all, the Gromov-Lawson surgery lemma could be improved to instead of considering the case where, basically that was saying if it admits a positive scalar curvature metric, then that is still true after doing codimension 3 surgery. And so Jimmy's lemma is that if the Yamabe invariant, or the sigma constant of the manifold, is greater than or equal to 0, then that remains true after doing codimension 3 surgeries. And then this boils it down to it's a question about spin cobordism. And I was very happy that I was able to tell him the trick he needed was to look at the Joyce manifolds as an extra generator in spin cobordism. It turned out that was exactly the magic bullet. So he asked the question, I said, well, why don't you try those? It turned out that just
dimension 8 or?
Yeah, but then you have products of those with other things in the spin cobordism. So it turns out that if you think of that as a generator in the ring, that was exactly the missing piece. Yeah. So that's a beautiful result. So it was phrased not in terms of this invariant, which I called I sub S, but rather in terms of the Yamabe invariant or sigma constant, which I have not discussed, but which I will discuss in a later lecture. Other questions? All right, so the question that Andre just asked was kind of on target, because the next thing we need to talk about is the Dirac operator in the spin case. So the point of view that I'd like to develop is that if you have an oriented four-manifold with a metric, then we emphasized before that there is this oriented rank 3 vector bundle, which has an inner product on it. Its structure group is SO3. So that's an R3 bundle over the four-manifold, and you can look at its unit sphere bundle. S of lambda plus would be looking at the unit vectors in that bundle. So it would be a 2-sphere bundle over your given four-manifold. Now this turns out to be an extremely important space, and if I won't be talking about twister methods in this course, but actually when you develop twister theory for Riemannian four-manifolds, it is on that 6-dimensional manifold which arises as a 2-sphere bundle over the four-manifold. So it happens to have an almost complex structure, but in fact, what I want to emphasize instead is the more obvious fact that this 2-sphere bundle, since it's a bundle of oriented 2 spheres with a fiber-wise metric, every fiber can be made into a CP1 just by saying, well, I can rotate in the tangent space by 90 degrees. So you can actually think of each of these as so you can think of this as a natural CP1 bundle over your four-manifold. Now, what is less obvious is that, in fact, you can always find a vector bundle. You can always find a rank 2 complex vector bundle whose projectivization, fiber-wise, is this 2-sphere bundle. This statement turns out to be, we'll see it later on, this is really saying that every four-manifold admits spin C structures. But in the particular case, if you assume that W2 is equal to 0, then you can actually find a preferred choice of this rank 2 vector bundle, who's with projectivization equal to that sphere bundle, but also having the extra property that its determinant line bundle is trivial. So it has structure group. It has structure group SU2. One can also do this same thing for the anti-self-dual 2 forms. And there is a companion rank 2 vector bundle whose projectivization is S minus, and where the determinant line bundle again will be trivial. Now these two bundles are actually, this is not the usual way of getting at spin structures on four-manifolds, but it does play up the fact that, remember we saw before that, that if you looked at SO4, then as a Lie group, you can think of it as SP1 times SP1 mod Z2. In other words, SP1 times SP1, topologically this is the 3 sphere times the 3 sphere. That's the universal cover of SO4. So if you take the double cover, if you like, as a definition, you could say that's SP1 times SP1, and SP1 is isomorphic to SU2. When you think of the 3 sphere as a Lie group, you can also realize that as the group SU2. So the issue of whether there is a spin structure on a four-manifold is the same as asking whether the principal frame bundle, SO4 bundle of, by looking at the bundle of orthonormal frames on the manifold, whether that has a double cover by a principal spin 4 bundle. In other words, if you can actually, so fiber by fiber, there's no problem saying, well, the double cover of the orthogonal frames at a point would be isomorphic to SU2 times SU2, but the question is, can you assemble that globally into a principal bundle? But thinking about it in terms of vector bundles, if you have a principal bundle which double covers the principal bundle of orthonormal frames with structure group SU2 times SU2, then SU2 has a standard representation on C2. This SU2 has a standard representation on C2. You can use those to build. Two different complex rank 2 vector bundles. You can avoid all of that in the following by the following trick. The trick is that let's let script V be the vertical complex line bundle of Z, which is the sphere bundle of manifolds. Okay, then having a spin structure is equivalent to having a line bundle which is a square root of this vector bundle V. So let's say it's V to the 1/2 in the sense that L tensor L is isomorphic to V. All right, so there is a complex line bundle on this 6 manifold consisting of, if you look at the things that are tangent to the fibers, that is, we've just said you can think of the fibers as complex curves. So there is a vertical complex line bundle, which I'm calling V. And the question is, can you write that line bundle as the square of another line bundle? is there another line bundle with the property that when you take its tensor product with itself, you get V. There's a calculation which shows that the obstruction to doing that is exactly the second Stiefel-Whitney class. It's not obvious without some long, but for example, if you look in one of my pages, you can find this computation. All right, so if you can take, a different way of saying what is this bundle V plus, this V is naturally a holomorphic. This V is fiber-wise holomorphic of Chern class 2. So this is on fibers. This V looks like O of 2 because the tangent bundle of CP1 looks like O of 2. And this L, if it exists, would be something that looked like O of 1. And so this vector bundle V plus, you could take it to be fiber-wise. Take the holomorphic sections of this L. So this is something of Chern class 1, it would have 2 sections. So that is a way of getting a more geometric picture of what a spin structure is. You have a vertical line bundle, does it have a square root? If it does, when you look at its fiber-wise holomorphic sections, that's a rank 2 vector bundle. Now you don't have, if spin structures are new to you, don't worry about this. But the real point is that when you construct these two bundles, S plus and S minus, so here I should have said S plus, not V plus. In the notation I've been using, this is S plus. So having such a line bundle is the same as saying W2 of the manifold vanishes. And that's not always true. We saw the distinction between spin and non-spin manifolds. We've seen a lot of examples before. The key thing is that if you construct these two vector bundles, S plus and S minus, they have various algebraic properties, and one of them is that the homomorphisms from S plus to S minus, so that would be S plus has rank 2, so it looks like C2 fiber-wise, so this would look like homomorphism from C2 to C2. In other words, this looks like the 2 by 2 complex matrices, that's a rank 4 complex bundle. Well, there actually is a rank 4 complex vector bundle that's already sitting around on a Four-Manifold. Take the one forms on the manifold and complexify them, right? So the real one forms, the duals of the tangent space, has fiber R4. If you complexify it, it has fiber C4. And the peculiar thing here is that there's a nice way of taking the model of that bundle to be homomorphisms from positive spinners S plus to the negative spinners S minus. So this is this actually is a way of explaining the basic theory of spinners in dimension 4 without explicitly using the theory of Clifford modules. So the algebra can be done in a completely different way. But one of the key properties about these spin bundles, S plus and S minus, so S plus is the one that you build out of the sphere bundle of, from this point of view, you're choosing it so that the sphere bundle of lambda plus is the projectivization of S plus, and the sphere bundle of lambda minus is the projectivization of S minus. And then it'll turn out that the homomorphisms from one to the other, that rank 4 bundle, can be thought of as the bundle of one forms on your manifold. So you get an actual so-called Clifford multiplication map. If you take the vector space of lambda 1 tensor S plus, make this here, if you like, I'm writing this is the tensor product over R, but that automatically complexifies lambda 1. So there's a map from lambda 1 tensor S plus to S minus, because what you can think of an element of lambda 1 as a homomorphism from S plus to S minus. Now you apply it to an element of S plus by contraction here. So that's the so-called Clifford multiplication map. On the other hand, you also, so there's a notion of parallel transport in lambda plus, and if you think about things in this way, that ends up, if this is your definition for S plus fiber-wise, that vector bundle would come automatically with a certain covariant derivative on it, induced by the Riemannian covariant derivative. So there is a covariant derivative on spinors. A section of S plus has a covariant derivative, which would be in lambda 1 tensor S plus. But then we just saw that algebraically, there's a nice map from lambda 1 tensor S plus to S minus. And when you compose these two operations, you get an operator that maps sections of S plus to sections of S minus, which is called the Dirac operator. So you first take the covariant derivative to get a section of lambda 1 tensor S plus, and then Clifford multiplication maps from there to sections of S minus. And this turns out to be a really important elliptic first order operator. The modern version of it in Riemannian geometry was first thought about by Atiyah and Singer. Although its origins go back to Dirac. Dirac was specifically thinking about 4 dimensions, but he was doing it in Minkowski space. And that was eventually generalized to curved Lorentzian manifolds by Schrödinger, but that literature was almost forgotten about. So there is a nice, if you're on a 4-manifold with W2 equal to 0, there is a beautiful map from the sections of the positive spinors to the sections of the negative spinors. And this is elliptic. So its symbol is actually positive in all real directions. So, or is invertible in all real directions. So, in particular, that implies that the kernel of the Dirac operator is finite dimensional. The co-kernel is also finite dimensional, and the difference of them is the index of the Dirac operator. In general, this in higher dimension, if you can do this on spin manifolds of dimension 4k for any k. The number here that would occur is usually called the A hat genus, but in dimension 4, it turns out to coincide with minus the signature of the manifold divided by 8. So a spin manifold automatically, well, this would just by looking at this would say, oh, you're on a spin manifold. That means the signature must be a multiple of 8. But there's something else that's true. Namely, because the structure group of so V plus and V minus over your 4-manifold, you could say, if you like, that the usual way is to think of these as complex vector bundles. The fiber is C2. However, there's also, remember, you can think of the structure group of each one as SP1. That's the group of quaternion linear maps. So if you want to, you could instead say, oh, well, this is actually a quaternionic line bundle. Each fiber is actually, we've been emphasizing it, it's a complex vector bundle, but you could actually make this into a complex vector bundle in a family of different ways. Each fiber can be thought of as a copy of the quaternions. And so the observation of Atiyah and Singer is that the kernel of the Dirac operator is a vector space over the quaternions. Namely, there is a there is an anti-linear map of the complex vector bundle S plus, which corresponds to multiplying by the quaternion J. That's parallel, it's invariant under parallel transport. And similarly, if you look at the kernel of the adjoint of the Dirac operator, or this is usually called the co-kernel, is also a vector space over H. That means, if you think of them as complex vector spaces, the complex, if it's a quaternionic vector space and you've just forgotten about J for a little while, it has to have even complex dimension. So the kernel of the index of the Dirac operator, meaning the dimension of the kernel minus the dimension of the co-kernel, and here we're taking the complex dimension. Well, this is a quaternionic vector space, so it has even complex dimension. This is also, so this is something even dimensional minus something even dimensional, and so that is even. The index of the Dirac operator is actually an even integer, but when you look at, so if this is even, that means that the signature is divisible by 16. And that's exactly what Rocklin had discovered by completely different methods. If you had a spin four-manifold, smooth spin four-manifold, then in fact its signature was divisible by 16. And it was this discovery about the Dirac operator, which apparently, Attila went racing up the stairs of the Mathematical Institute in Oxford, yelling at the top of his voice to get Issinger's attention, and said, "I've just discovered this proof of Rocklin's theorem," using what they had been doing on the index of elliptic operators. And so this was actually one of the key moments in the discovery of the index theorem. So, for example, we saw before that the signature of the K3 surface was minus 16, and that really the kind of topological models you could think of simply connected spin manifolds would be connected sums of K3s and S2 times S2s. In all cases, you get that the signature is divisible by 16. All right, so this is something that has a geometric origin related to the geometry of the Dirac operator. Now, there is a fact, actually curiously, it was kind of known to Schrödinger, but Schrödinger was not thinking about elliptic operators. He was writing down the Dirac operator on a curved Lorentzian four-manifold, implicitly assuming that it was spin. Lichtenowitz discovered that, in fact, there's an amazing Weizenbach formula for the Dirac operator. And it's actually a misnomer to call these things Weizenbach formulas. It turns out that Weizenbach never really wrote down any Weizenbach formulas. It was the French school that named them Weizenbach formulas, even though actually Weizenbach was notorious for the fact he hated France after World War I. I don't know why they decided these things were called Weizenbach formulas, but there are all kinds of interesting formulas where you take a geometric first-order operator, you compose with its adjoint, and then it turns out that you get something that is basically of Laplace type. So one version of this Weizenbach formula, there's a simpler version which I should write down. Here So the thing that Lichtenowitz actually discovered is that if you take the Dirac operator and you compose with its adjoint, then this is sometimes called the rough Laplacian, of course it's associated with the covariant derivative. And if that was, so this is sort of surprising that there's any relationship, but the point is that these have the same symbols, and it turns out that the extra term is just a zeroth order term. So the extra piece is you multiply by the scalar curvature. Here, you'd be thinking about this in terms of formal adjoints of these operators, but it turns out in both cases, this is really just minus the covariant derivative for the contraction. This is really the analog of the Dirac operator for the other orientation. These are very nice things. When you put them together, when you take a section, apply d star d to it, and then take the inner product with phi, then actually what's left over, you can now simplify this as, well, there's one term which involves the covariant derivative of phi squared. There's another which is the length of phi squared times the scalar curvature before, and then there's the leading term is then half of the positive Laplacian times phi squared. So one consequence is that if M is a compact spin manifold with non-zero signature, that would then, by the previous observation of T.M. Singer, say that, well, the index of the Dirac operator is non-zero, then, in fact, there can't be a metric of positive scalar curvature on M. So, for example, suppose that M is a K3 surface. We've seen K3 has non-zero signature. The signature is minus 16. You could ask, does K3 admit a Riemannian metric of positive scalar curvature? And the answer is that's impossible, no. So why? Why is that true? So what you would do is so it's also worth noting that if you instead take the adjoint, you could also say what would happen if you took the composition of d star and d in the other order, then you would get the same formula. These are really the same operators for the two different orientations. So this is on S plus, and this would instead be on S minus. So, for example, the signature of K3 is minus 16. The index, therefore, is plus 2 for a K3 surface. Therefore, there must be something that's in the kernel. The kernel, if this is positive, it's plus 2 for a K3 surface, then the dimension of the kernel must be positive. Now you take such a thing, you plug it into this formula, and for example, you could apply them at the, what happens at a maximum? Well, at a maximum, because this is the positive, so this is minus the trace of the Hessian, at a maximum, this is positive. So, so at a maximum, this is positive. This is certainly positive. The scalar curvature is positive. I mean, this is all non-negative, right? But on the other hand, if you have something that's in the kernel of Dirac operator, this would be identically zero. And you're saying that it's everywhere non-negative. Well, that can only happen. I mean, this term would definitely be strictly positive if the scalar curvature was positive and phi was not identically zero. So you read off from this that on K3 surface there can't possibly be, you can't have a metric of positive scalar curvature. The scalar curvature has to be zero or negative somewhere. You could even push that a little bit further. Suppose that you had a metric where the scalar curvature was zero on K3. You know, Claude metric has that property. So this last term would go away if the scalar curvature was identically zero. But then you would find, well, this phi would have to be parallel. Its covariant derivative would have to be, you could just integrate this on the manifold, you'd find that the integral of this covariant derivative squared would be zero. The covariant derivative has to be zero. And so what you'd find is the only zero scalar curvature metrics on a K3 surface are actually Calabi-Yau metrics, where the polynomial is reduced by having a parallel spinner. Okay, so Lichtenhorst also made this statement more generally about the A hat genus, which is the index of the Dirac operator in higher dimensions, multiples of 4. So there are, this was a discovery in the early 60s, that there were lots of smooth 4 manifolds, and in fact also 8 manifolds and 12 manifolds and so forth, which don't admit positive scalar curvature metrics. And that is a theorem that a lot of people found very, very frustrating, because there are some people in Riemannian geometry that think all things should be kind of provable by completely local methods. Here you really are using some global analysis, the index of the Dirac operator. And other things that we'll do will build on this. So this was the first discovery that there were 4 manifolds that don't admit positive scalar curvature metrics. Okay, so K3 does not admit a metric of positive scalar curvature. And we could also look at that family of things we discussed before. If you take a smooth hypersurface of degree n, its spin, if and only if n is even. So if you look in terms of the formula for the signature for m even, you'll see directly, just without knowing Rockland's theorem, you find out that the signature is actually, just by doing the computation blindly, you find that the signature turns out to be minus 16 times m plus 1 choose 3 divisible by 16. So, so in particular, this formula for the signature, it's non-zero for all m. If n is greater than or equal to 4, these are spin manifolds which do not admit positive scalar curvature metrics. Now, one peculiarity about this, though, implicitly, we're using the smooth structure in order to talk about elliptic operators, and this argument uses a particular smooth structure. But actually, if you had another smooth manifold which was homotopy equivalent or homomorphic to one of these manifolds, well, the signature is a homotopy invariant, and so you would and being spin turns out W2 is a homotopy invariant by Wu's formula. So in fact, even though this uses the smooth structure of the 4 manifold, it actually is ultimately a statement about the homeomorphism type. So no matter which smooth structure you choose on a K3 surface, it has exotic smooth structures, it turns out. None of those have positive scalar curvature metrics. So on the other hand, we could ask, about what, this is my favorite family of examples to give you of some very concrete 4 manifolds arising as complex surfaces. If these have, if the degree is odd, so for example, what if it's a quintic hypersurface or a septic hypersurface, degree 5, degree 7 in CP3, does the corresponding manifold admit positive scalar curvature metrics? Now, if we were not focused, this is a smooth manifold. It has a given smooth structure. It's one that's just naturally occurring because it's given to you as a smooth manifold. If we were to use Friedman's theorem for n equal to odd, this is a simply connected manifold. If it's non-spin, Friedman says that actually the homeotype is just a connected sum of a certain number of copies of CP2 and a certain number of copies of CP2 bar. CP2 admits a positive scalar curvature metric. Fubini-Suri metric is an example. If you reverse the orientation, that statement about positive scalar curvature has nothing to do with orientation. There's a little surgical limit that's really underlying the Gromov-Lawson result. Taking connected sums, an example of codimension 4 surgery. Positive scalar curvature is preserved under these taking connected sums. So, connected sum of a bunch of CP2s, a bunch of CP2 bars, there are metrics of positive scalar curvature. Right? When n is 4, there is some smooth structure where there's no positive scalar curvature metric. But what about this smooth structure? If it's given as a hypersurface in CP3 of that degree, well, I claim for that smooth structure, there are no positive scalar curvature metric. And that's an example of the fact that these manifolds have different smooth structures. So we need to talk about spin C structures in order to set up this theory. And the first thing that we need to observe is that W2, the second Stiefel-Whitney class, turns out to always be in the image of, it's always in the image of the integer cohomology. And that's not obvious. It's obvious in the simply connected case because the next thing in the sequence would be H3, which is dual to H lambda 1. But even if H3 has two torsion, it's a non-trivial fact that the second Stiefel-Whitney class always has integer lifts. If you have such an integer lift, well, that means you can find a line bundle whose Chern class reduces mod 2 to the second Stiefel-Whitney class. And so we could now do the following thing. Given a metric G on M, you could look at, there's always a rank 2 Hermitian vector bundle, V plus, and another partner bundle, V minus, which formally would look like the spin bundles. So the spin bundles actually don't exist if W2 is not 0. If W2 is not 0, the square root of the line bundle L does not exist. But locally, you could pretend that it does exist. Right? So locally, restrict, there's no topological obstruction if you restrict to something that's like a coordinate chart, which is diffeomorphic to R4. And now you could say, well, if I try to glue one of the transition functions that such an object would have, so up to sine, there is a well-defined transition function for S plus. Up to sine, there is a well-defined transition function for the square root of L. So you take the transition functions for L and take their square roots. There's a sign ambiguity here. There's a sign ambiguity for the transition functions from S. And this statement actually says that the signs cancel. You can come up with global vector bundles, which formally are of the type S plus tensor L to the 1/2 or S minus tensor L to the 1/2. I'm going to make this concrete now, so that that sounds like some kind of boondoggle. Here, I'm going to make it completely concrete. Suppose we're on a manifold where we have an almost complex structure. Right? If we're talking about complex surfaces. They have certainly complex structures. You could just treat those as almost complex structures. And then if you have an almost complex structure, it has a 0, 2. This would be the anti-canonical line bundle of that structure. Take L to be the bundle of 0, 2 forms for that given almost complex structure, where we're taking our metric to be just invariant under the given almost complex structure, which you can just arrange by averaging. All right, so here are two completely concrete real two C2 bundles. You can take the bundle of 0, 0 forms, that's just C. This is the anti-canonical line bundle, and then you can take the bundle of 0, 1 forms. That actually is the same as a complex vector bundle. It's the same as taking the 1, 0 tangent bundle. And then the point is that these can formally be written as S plus or minus tensor L to the 1/2, where L is this vector bundle. Okay, so in fact, when we look, so there is a version of the Dirac operator. I didn't mention it before. If you have when does if you have an almost complex structure, when does W2 vanish? It's if and only if there is a square root of its C1 has reduction mod 2 to be 0. That's to say it is divisible by 2, And so you can take the square root of the anti-canonical line bundle. And in the spin case, then in fact, this would be, you could transfer this to the other side, say s plus or minus is, there's a square root of the canonical line bundle, twist these two very concrete vector bundles by that line bundle, which would actually be a holomorphic line bundle or a complex manifold. Then you can look at the d bar complex, look at d bar plus d bar star. Strictly speaking, you should multiply this operator by the square root of 2. That literally on a Kähler manifold would become, on a Kähler surface which has a spin structure, this, the Dirac operator I was talking about literally becomes the square root of 2 times d bar plus d bar star for the complex associated with, it's really for the Dolbeault complex. You would have d bar and d bar star operators for these twisted by a certain holomorphic line bundle. So if you're not familiar with Dirac operators, a really good test case to work with is to take so if MGJ is Kähler, and this has real dimension 4, so this is a complex surface, then you have this Dolbeault complex that would, so if it's spin, this is the same as saying that C1 of the manifold is twice some other class A, and you could say that A be the first Chaire class of some line bundle L, and then what you would find is that your Dirac operators, you could take the spin bundles to be, well, the 0, 0 forms plus the 0, 2 forms twisted by, so this allows you to define, let's call this the dual of the canonical line bundle. And then you would be, you have there's a line bundle, Kähler 1/2, with the property that its square is the usual canonical line bundle. S minus, same thing for the 0, 1 forms with values in Kähler 1/2. These would be holomorphic line bundles, and you would have an associated, the Dolbeault complex. So you have the sections of 0, 0 forms with values in Kähler 1/2, and a d-bar operator that lands in 0, 1 forms with values in Kähler 1/2. You would have then a map to 0, 2 forms with values in Kähler 1/2. And then this operator has an adjoint. And so the sum of these two has a map to that. D bar plus D bar star maps what I'm calling the sections of S plus, so it's this bundle, to the sections of S minus. And if you up to a factor of 2, this is exactly the Dirac operator of your Kähler manifold. So if you want to, if you're skeptical about this and you want to understand the relationship between, what do spinors mean concretely on a Kähler manifold that is spin in real dimension 4, or even higher dimensions, it turns out this has a generalization to higher dimensions. This was really Nigel Hitchen, in his thesis, made significant use of this concrete realization of the Dirac operator. All right, so if you think of the d-bar operator in complex function theory as being something that is familiar, but the Dirac operator is unfamiliar and seems strange, and you think it's some kind of science fiction. Here is a setting in which, really, if you understand the d-bar operator, the Dolbeault operator, and its adjoint, then you actually have already been dealing with a version of the Dirac operator. So the other thing that's really nice here, I've been saying, well, you could if you happen to be on a Taylor manifold, then you can imagine making different choices of this line bundle, and it's really just twisting this complex by different holomorphic vector bundles. You can even do it when it's not a holomorphic line bundle. Okay, so twisted versions of this would be these would give rise to these spin C Dirac operators. So the real difference between this theory and the previous theory of the Dirac operator is that you don't for free get, there's actually a choice of a connection on the line bundle L that you need. So if you have a connection on L, then this bundle V plus, which is formally the spin bundle twisted by L to the 1/2. The spinners naturally, even locally, they make perfectly good sense. Locally, L to the 1/2 makes perfectly good sense. If you're trying to make sense of this covariant derivative, you need a connection on L in order to be able to define it. So there's a choice of connection on L that's necessary to make any progress, to get anything out of this. But if you choose we'll think of L as having a fixed inner product. We choose a connection on that line bundle, which is a complex line bundle, and we choose a connection on it that is compatible with its inner product. Then we get, essentially in the same way as before, the definition of the way that we constructed the Dirac operator by composing a covariant derivative with Clifford multiplication carries over in this case. And you can even say, well, what's the analog of the Weizenbach formula? The Weizenbach formula we saw before, actually in the spin case, looked like this, but there's an extra term that crops up in the general case. So if L is a non-trivial line bundle, you also, it typically has non-trivial curvature, and here you get an inner product between the curvature, the self-dual piece of the curvature of L, and a quadratic expression, depending upon the spinner. And this quadratic expression has the property that, so it's quadratic in the sense that the norm of sigma of phi is actually is phi squared times 1 over the square root of 8. So there are various. So in fact, if you look at this famous paper by Hitchin from the 1970s, he was aware of this story, right? So he knew that you could use spinners to rule out the existence of positive scalar curvature metrics, but the problem in this theory is that this Weizenbach formula, it does so the scalar curvature is a property of the Riemannian metric, but this is something about the line bundle, this curvature. Well, you chose some connection, you don't know anything about its curvature. And so this was a limitation for him. So he was, in the last part of his thesis, the last part of his published paper, he's thinking about this, but he doesn't see how to get a very good result about the scalar curvature of Riemannian manifolds. A breakthrough then happened in the mid-90s when Ed Witten said, let's consider not just the kernel of the Dirac operator, but then we have some connection to choose on the line bundle. And the idea was not to think of the spinner as the only unknown, but to say the connection on the line bundle is also an unknown. And the particular clever pair of equations he considered is, so let phi be killed by the Dirac operator associated with that particular connection in the line bundle. And the other thing is require that the self-dual piece of the curvature of the connection, require that be I times this quadratic expression sigma of phi. Now, this last equation is nonlinear, right? So because sigma of phi is not, the two variables here are phi and the connection A. The first this is linear in A, it's linear in phi. The second thing is actually not linear in phi, although its dependence on A is still linear. So so this is a mildly nonlinear elliptic system with a pair of PDEs. So this is elliptic in the sense that if you choose these are geometric equations. If you take an arbitrary automorphism, you take a function from the manifold to the circle, you think of that as a unit complex number, you can act on the line bundle by multiplying by that, pull back, you'll get a new connection. It's basically geometrically the same. You can eliminate that by imposing a gauge fixing condition to say that choose some background connection and require that your new connection has the property that the difference between the two is co-closed. So this gauge condition is a little bit analogous to when I first started discussing Einstein metrics and wanted to rule out diffeomorphisms, generalizations of trying to say in a given coordinate system require that the coordinates be harmonic. This is a similar kind of condition. It's called a gauge fixing condition. So that eliminates the automorphisms on L. It cuts them down from an infinite dimensional space to something that basically looks like the circle times a discrete group. And now, actually, the Weizenbach formula has been, that very clever choice of the two equations now means that the Weizenbach formula, the last term would have involved an inner product between something quadratic in phi and the curvature of the line bundle. But here, the curvature of the line bundle is phi itself. So this ends up being, you got this very, very positive kind of Weizenbach formula. If you have a solution of those equations, why would you have a solution of those equations? We'll come to that. Suppose for a moment you have one, then in fact the Weizenbach formula that the spinner satisfies is that twice the Laplacian of phi squared plus 4 times the covariant derivative of phi squared plus the scalar curvature times phi squared plus phi to the fourth is 0. And the first application of this is the moduli space of solutions of these equations for a given metric and a given spin C structure is actually finite dimensional. So the reason is it's a bootstrap argument. You can use a so the key thing is it basically uses relish theorem. If you've got want to claim that there's a universal bound on phi, and that gives you bounds on this connection up to gauge fixing. So when if we assume our manifold has B plus at least 2, then as the metric varies, we have some finite dimensional moduli space, and it varies in a nice way. The moduli spaces are actually coordinate, and so you can construct invariants that sometimes predict the existence of solutions. So specifically, if we chose I just told you how some spin C structures actually come, if you have a choice of almost complex structure, that gives you a spin C structure. It'll turn out that the Fredholm index for the system is then 0, the moduli space is generically discrete, and for example, if you count the number of solutions mod 2, when everything's generic, you get a Z2 mod valued invariant. If that invariant is non-zero, then that's predicting that you must have solutions for any metric. And so this invariant turns out to be non-zero for complex surfaces with B1 even. And that will in particular imply non-existence results for metrics where the scalar curvature is positive, specifically on any complex surface where B plus is bigger than 2. All right, so this condition, so b plus equals to 1, the theory is much more complicated. Oops. So when you're looking for, there's a mechanism, Seiberg-Witten theory, which allows you to prove things like all of those non-spin complex surfaces we were looking at by taking hypersurfaces where the degree of the hypersurface in CP3 is bigger than these high degree complex surfaces which were non-spin. Seiberg-Witten theory actually gives rise to a method for showing that they don't admit positive scalar curvature metrics, but it will show more. It'll actually one consequence is that you still get a result when b plus is equal to 1, and it turns out that the only complex surfaces that can have a Riemannian metric with positive scalar curvature on them actually have the property that the Kadeira dimension is minus infinity. Okay, so the place we've been moving towards is to understand which smooth complex four-manifolds admit Einstein metrics. We've just seen that Taylor geometry provides lots of examples, and we would like to I seem to be touching the self-destruct button or something.
You turn off the Wi-Fi out.
That's funny. But that's a very good idea. Let's see. But I'd have to do that. I'd have to get out of here. Yeah, I can do that. But yeah, I think it's not a good idea. It's going to be too complicated. I'll just have to try to live with this for a moment. Okay. Yeah, it's just in the wrong place now. Okay, so the things we've been talking about is which smooth compact four-manifolds admit Einstein metrics. What I want to focus on is the special case. If you have a smooth four-manifold, which happens to be the underlying smooth manifold of a compact complex surface, when does that four-manifold admit Einstein metrics? Unrelated, so those are not assumed to have anything to do with J. And I'm sorry, this is repetition I should cut out. All right, so as I've said, the key structure is that we can take any almost all right, I agree. I need to get out of here and shut down the Wi-Fi. All right, so the thing that we've been building up is that if you have an almost complex structure on a four-manifold, you can actually give it a very specific spin C structure. But concretely, the two spin bundles are the bundles of 0 even and 0 odd forms. So when I say 0 even, it's the form of sum of the 0, 0 forms and the 0, 2 forms, and the 0 odd would be the 0, 1 forms. All right, and so to say that a spin C structure arises from some J turns out to be exactly the same as saying that C1 squared of the line bundle. So if you have a spin C structure, there is a line bundle L, you can look at C1 squared of it, and we already saw that a necessary condition would be that 2 chi plus 3 chi is M of M is the same as C1 squared of the line bundle, but the converse is also true. All right, so so we've just seen that. So I just indicated before that this Weizenbach formula plays a crucial role, and let me now show you how. It turns out the moduli space is necessarily compact because this implies a C0 bound on the spectrum. If you have a solution of the Seiberg-Witten system, so phi is in the kernel of the Dirac operator, and then there is the curvature is this quadratic expression in phi. That implies that we actually get an L infinity bound, a C0 bound on the spinner phi. And the trick is that at the maximum, with this, with the sign of the Laplacian that I'm using, this is the positive spectrum Laplacian, at a maximum, the Laplacian of phi squared is greater than or equal to 0. And so that ends up saying from this Weizenbach formula, at a maximum, this would be positive. Certainly that is, this would be non-negative, this is non-negative. And so what we find is that S times phi squared plus 5 to the 4th has to be non-positive. And reading off from that then, you find that, well, unless phi is identically 0, at its maximum, phi squared is less than minus the scalar curvature. Okay, so you find that the norm of phi is less than the maximum of the absolute value of the scalar curvature, and in fact, you could just say, don't worry about the whole scalar curvature, just take its negative part, see where that's absolute value is biggest. So take the point where the scalar curvature is the most negative, take its absolute value, the square root of that is an a priori upper bound for any solution of the Seiberg-Witten equations. Now, what you can then do is you take the fact that we go back and look at what the system actually looks like. If we have an L infinity bound for phi, we get an L infinity bound for the curvature, and that's basically dA. We've also got d star of a minus a0 is 0, and that ends up actually giving rise, that's a first order equation. You can then read off an LP1 estimate for a minus a0, then you put that back in the equation. This would give you then control on, you have this expression involves A, you plug in, and you keep bootstrapping, and you find that you keep iterating this procedure, and you get LPK bounds for the pair phi and A for any K and any P. So in particular, what we want to then, so the moduli spaces are always compact. We also want to say that they're finite dimensional. So the index of the gauge fixed system, if we look at not just the Seiberg-Witten equations, but also impose this gauge fixing condition, that pair is actually an elliptic system of PDE, and the index there would predict that the index is C1 squared of this line bundle minus 2 chi plus 3 tau of M divided by 4. But in the case that we're looking at, if L came from an anomalous complex structure, that's the case I've been concentrating on, C1 squared of L would be 2 chi plus 3M. And so this would say that the index is actually 0. But even if we considered it for other other topological choices of L, we would still find that there would be, if we knew the first Chern class of L, we would get an estimate for the dimension of the moduli space. The problem is the moduli space might not be smooth. So in what sense are we really calculating this is asking about if we take the linearization of the system, what if we happen to choose a line bundle so that C1 squared of L is 2 chi plus 3 tau, this Fredholm index would be 0. We will eventually look at some cases where where instead C1 squared of L is bigger. But right now, let's just consider this simple case. Classical case is to take an almost complex structure, determine. Suppose you have an almost complex structure. Use it to determine your spin C structure, and then this index of the system will be 0. And so in this case, the prediction would be that if we take a generic perturbation of the equations, we should just get a discrete set of solutions. And then the way that one defines this invariant is actually analogous to the way you define the mod 2 mapping degree in the classical setting. All right, so if so the tricky point here is that in order to eliminate the possibility, the real question is, as you vary the metric and you choose different, for fixed spin C structure, as you vary the metric, can you show that these moduli spaces are covariant? The condition that you need is the non-existence of reducible solutions where phi is identical to 0. You can arrange for that as long as you assume that b plus of n is bigger than 2. So, so what you basically do is count solutions of the Seiberg-Witten equations mod 2 for example, find some choice of metric where you could count these specifically, where you could find all the solutions and enumerate them, and then you would be able to read off from that example what this invariant is, and then you have this topological argument which would say that as you vary the metric, well, you would still have the same invariant. If it's non-zero to start with, it would have to be non-zero for other metrics. All right, so the typical example is that it's non-zero for, if you take a complex surface of Kähler type, you take the integral complex structure as your example, use a Kähler metric, and as your prototype, you can actually solve these equations explicitly, and you find out that counting solutions, well, the count is 1 mod 2. In fact, it's even 1 over the integers. So, so you end up with a non-existence of metrics, in particular for which the scalar curvature is positive. So b plus is equal to 1 is more complicated, but there is one setting in which the theory works exactly in the same way. We could assume that C1 squared, our choice for L, suppose that C1 squared of L is positive. If that's true, then you can eliminate, the equations would then say you couldn't have a solution where phi was identically 0, because it would end up saying that C1, that L was flat at that solution, and then this would be a contradiction. And you can also get the same trick works if you assume that C1 squared of L is 0, but that C1 of L is not 0 in the real cohomology. All right, so in other words, if we're looking at things that might have if we're looking at things that are rows as complex surfaces, and we want to ask, is complex surface have any Einstein metrics on it. Hitchin-Thorpe, C1 squared of L would be 2 chi plus 3 tau, and we would know in most cases that C1 squared of L would have to be positive. All right, so here, what is that we want to do to improve this Hitchin-Thorpe inequality? The Hitchin-Thorpe inequality depends on this argument that if the trace-free Ricci curvature is 0, then 2 chi plus 3 tau has to be positive. But actually, suppose we had a non-trivial estimate for the integral of the scalar curvature squared, which is where we began in this lecture. If you can find a non-trivial estimate for the integral of the scalar curvature squared, you improve the Hitchin-Thorpe inequality. Or maybe you can find a non-trivial estimate for this, which is that comes from a different source. Then that would improve the Hitchin-Thorpe inequality. Rather than just saying that this has to be greater than or equal to 0, if you can get some a priori lower bound on this, which is positive, then you've improved Hitchin-Thorpe. So the sorts of things that one can use, but these tricks show that if the Kadir dimension is greater than or equal to 0, you can actually show that the Seiberg-Witten invariant for the given the complex structure determines the spin C structure, and the claim is the Z mod 2 Seiberg-Witten invariant is non-zero for the one that comes from the complex structure. All right, so here's the basic application of this. Suppose we have a compact complex surface. If the smooth compact four-manifold admits an Einstein metric G with lambda positive, then you want to claim that the Kadir dimension is minus infinity, and that the manifold has to be diffeomorphic to either connected sum of CP2 with at most 8 CP2 bars, or S2 times S2. Now, these are the so-called Del Pezzo surfaces in terms of the diffeotypes. We'll come back to these. But what's the key point? The Seiberg-Witten theory would say that if the Kadir dimension was greater than or equal to 0, you find that this Seiberg-Witten invariant would actually be non-zero. You couldn't have a positive scalar curvature metric, but here we've assumed that we have an Einstein metric where the scalar curvature is positive. And so there's one other thing. So this would be when you list the things of Kadir dimension minus infinity, I already mentioned that in the case where when B1 is odd, you find out by Hitchin-Thorpe there couldn't be an Einstein metric. These have to be things where B1 is even. You can list the diffeotypes. They're either S2 bundles over a curve, or they are, then you could blow those up, or CP2. This is the blow up of CP2 at K points. The other thing, how many points can you blow up? Well, 2 chi plus 3 tau has to be positive when every time you blow up, 2 chi plus 3 tau goes down by 1. So the fact that C1 squared has to be positive says you can't have too many blow-ups here. These are the only diffeotypes among the standard complex surfaces that could possibly carry a lambda positive Einstein metric. We'll see it later on. This is sharp.
Simply connected?
It follows that they're, lambda positive G would automatically imply that the fundamental group is finite.
Yeah.
But I haven't even used that here, so there's a different way.
You can have portions of S like RT2, no?
Yeah, not with a complex structure. So when you list the so I'm assuming the manifold is a complex surface, right? So among those that are candidates here, so you would know that C1 squared was positive, and the Kadir dimension is minus infinity. There's a different way of reading off from this that the fundamental group is finite, but you don't even need that in this argument. Surface classification would also tell you that the fundamental group trivial. All right, but this is just a very, very mild use of Seiberg-Witten theory. The use there was just saying not very many complex surfaces admit positive scalar curvature metrics and satisfy the Hitchin-Thorpe inequality strictly. But here's the deeper part of the theory. We want to try to get, for example, non-trivial lower bounds on the integral of scalar curvature squared. That was implicitly what I was talking about at the beginning of the lecture, right? I was talking about, can you find a non-trivial lower bound on the integral of the scalar curvature squared? That was the whole project for finding these estimates on I sub s. And so here are two basic curvature estimates that come out of the Seiberg-Witten equations. What follows, actually, it's just a matter of assuming that you have a metric where you have a solution of Seiberg-Witten, and it doesn't even use directly the mechanism that you use to predict that you have solutions, right? So we have two toolboxes here. One is a mechanism for trying to predict that Seiberg-Witten has a solution. The following argument basically is saying if Seiberg-Witten has a solution for a particular metric and a particular spin C structure, there are consequences about curvature. And they are the following. You find right now that the integral of scalar curvature squared has to be bigger than or equal to 32 pi squared times C1 of L plus squared. And there's also another estimate which is much harder, but which I found much later, which is that if you take the L2 norm not of the scalar curvature, but L2 norm squared, but instead of S minus a certain multiple of the pointwise norm of W plus squared, that there is a lower bound also for that with a coefficient that's bigger. Here the scalar curvature tends to be negative, so this minus sign, you're subtracting something, this is making it more negative, the coefficient turns out to be bigger. So the specific, the specific hypothesis is, suppose you have a metric, and for every metric in its conformal class, every metric which is G multiplied by a function, then you get these two estimates. You actually only need it for one metric to get the first estimate. For the second one, you're really implicitly using it for all metrics conformal to G. But you don't, that's somehow a very weak thing. What is this expression C1L plus? So C1 of L is an element of the second cohomology. But remember, harmonic theory says for a given metric you can split the cohomology into, like harmonic representatives, you can split the cohomology into self-dual and anti-self-dual harmonic forms. And this expression is C1 of L is some element of the second cohomology, project it into H plus with respect to this product decomposition. And if you like, this is exactly the same as taking the projection with respect to the intersection form. The intersection form on H2, these guys are actually perpendicular with respect to the intersection form, and you're taking the projection of C1 of L into C1 of L plus. So in the simplest cases, for example, so here, if we happen to be, and it's very rare, if you happen to go on a manifold where B minus was 0, this would just be C1 of L. But usually the projection is a crucial part of this mechanism. So it's not directly now, the estimate is in terms of the self-dual part of C1. So to get the first estimate, we have this Weizenbach formula. If you integrate it, so the first term is Laplacian something, that's a divergence term. So when you integrate, you don't see that anymore. And now you have, well, the first term is the norm of the derivative of phi with respect to this connection, but this is certainly greater than or equal to 0, so you find that you get the surprising estimate that the integral of the scalar curvature times phi squared plus phi to the fourth is non-positive. And you could turn that around to say that the integral of minus s minus the scalar curvature times phi squared is bigger than phi to the fourth. But now use the Cauchy-Schwarz inequality on the left-hand side. You find that this is saying the L2 norm of scalar curvature times the L2 norm of, or the integral of phi to the fourth to the 1/2 is greater than the integral of phi to the fourth. Well, if phi is not identically 0, you can cancel and just say that the integral of s squared is greater than phi to the fourth. If phi to the fourth happened to be identically 0, well, you'd also, you would know this automatically. If that were 0, there's nothing to say. But you could also say, the Seiberg-Witten equation, say phi to the fourth is the same as the norm of the self-dual part of the curvature up to a factor of 8. And this is bigger than or equal to the harmonic representative, the self-dual part of the harmonic representative, and that gives you this inequality. The integral of s squared is greater than 32 pi squared times c1 plus squared. But when does inequality, where does equality occur? So if you trace back, if you had equality, if you had equality in this case, that would mean that this term is 0. In other words, phi is parallel. And you would also find, we use Cauchy-Schwarz, so you'd also know that the scalar curvature would have to be constant. But this means that you're actually saying that the holonomy of, so sigma of phi would then be a parallel section of, so if phi is parallel, so is sigma of phi. That's a parallel self-dual 2 form. If it's not identically 0, then that says that the metric is Kähler. And you find that the metric is constant scalar curvature Kähler. And you also would find that A is the so-called Chern connection on the n-canonical line bundle. In particular, you find that there's just one solution. So actually, there's a way of using this argument backwards. If you started with a metric which was constant scalar curvature Kähler, you can work backwards and find that, well, there's only one solution of the equation, which is parallel. And then you would find that, well, there's just one solution up to gauge equivalence, counting mod 2, the Seiberg-Witten invariant is non-zero if there's a constant scalar curvature Kähler metric on your Kähler manifold. Now, there's a more robust version of this solution, which actually would just say if you have a Kähler metric for which the integral of the scalar curvature is negative, then you can do this counting argument with a little bit more freedom. I don't want to have to go through the details here. So that works actually as long as you're on a complex surface where C1 dot omega is non-zero for your, where omega is the Kähler class. Second estimate is much more subtle. And the point is that I haven't emphasized that the Dirac operator has a certain conformal invariance. But the Seiberg-Witten equations are definitely not conformally invariant, because what happens is that if you rescale the metric, there is a way of turning a solution. You can rescale your spinner in such a way to get something that's harmonic, but you've changed the formula for sigma of phi changes. It depends on the new metric. So if you multiply your metric by f to the minus 2, where f is a positive function, then with respect to the old metric, the Seiberg-Witten system turns out to be equivalent to, so one thing that always kind of worried me, well, why did Witten put a 1 here? What happens if you put a different constant? How about multiplying this second thing by f? It turns out that's equivalent to just conformally rescaling the metric. And so if you go through the argument again, the Weizenbach formula comes out almost the same, but there's an f in front of this 5 to the 4th term. And so if you go through and you multiply by phi squared now and integrate, you get this integral Weizenbach formula, which is going to tell you that, so here, the first term, if you multiply this by phi squared and integrate, that's positive, so, or non-negative. So you would get this very interesting Weizenbach formula. And so if you look at the self-dual 2 form, which is sigma times 2 square roots of, sigma of phi times 2 square roots of 2, this is a Weizenbach formula for that 2 form, which says that 0 is bigger than its covariant derivative squared plus the scalar curvature times the 2 form squared plus f times the 2 form cubed. And we can play a very similar argument. The point is that any self-dual 2 form, just by using the Weizenbach formula for the Hodge-Laplacian, it satisfies that its covariant derivative squared is greater than or equal to minus 2 scalar curvature over 3 plus 2 times square root of 2/3 times w plus times phi squared. So the Weizenbach formula for the Hodge-Laplacian involves Laplacian, there's a rough Laplacian plus a scalar curvature term plus a self-dual Weil curvature term. You put these together, you get this automatic inequality for any self-dual 2 form. And so using the formula we had before, this involves the covariant derivative of phi squared. We want to trade that off for curvature, and we get this inequality by using the Hodge-Laplacian's Weizenbach formula. And now you can manipulate. This is saying that minus the scalar curvature square root of 6 w plus times phi times the 2 form psi squared plus 3 halves to f psi cubed. That has integral less than or equal to 0. Now, instead of the Cauchy-Schwarz inequality, we use the Holder inequality to say that we have an inequality between the integral of f to the 4th to the 1/3 and this inner product of f minus 2 and scalar curvature of square root of s minus square root of 6 times pointwise normal of psi cubed. Strange formula, bigger than or equal to 9/4 f squared psi squared d mu. But psi times f is a representative for the self-dual part of, so this side, we get a lower bound for that, 70, it's 9/4, 32 pi squared, c1 plus squared. Now we have this jump on the other side. What do? Well, f could be any function we like. So we choose a sequence of functions fj, which are bigger than the square root of the absolute value of s minus square root of 6 plus f plus. And now in the limit, so that would end up saying, well, this fj is bigger than that. So this is something where we get an inequality on this and that squared. And we take this is also the same thing. So we find that if we take the limit, this sequence of f's approaching this function from above, what you find in the limit is that the integral of s minus square root of 6w plus squared must be bigger than or equal to 72 pi c1 plus squared. It's a little more delicate here to analyze the boundary case, but it can be done. All right, so we're about done for today. So right now, I've proved some estimates, which these are curvature estimates for the scalar curvature or for another function that involves the scalar curvature and the self-dual Weil curvature. But it's not yet in terms of so C1 plus still is a bit metric dependent because it involves the self-dual A self-dual decomposition. So next time I will show you how these estimates can, right now we have not yet gotten something that clearly just is in terms of the topology of the manifold M. And so there's more work to be done to go from these estimates to getting lower bounds for the integral of the scalar curvature squared, and for this expression involving the scalar curvature squared and W plus. I'm sorry that this gets quite technical, but I'm hoping that at least if you get the flavor of the subject, then that would mean you would be prepared to go into the literature and actually go through the proofs and see how it all works. But the point is that these amazing Seiberg-Whitney equations on suitable four-manifolds actually give rise to non-trivial lower bounds for things like the integral of scalar curvature squared. And I'll finish up that story in the next lecture. See you then.